Welcome. Today we begin Chapter 2, and we look at 2a, which is the basics of set theory. 4 big points that we'll hit: describing sets, basically what is a set, number sets, set builder notation, and then a few more definitions. There are lots of definitions in set theory, but it's okay, we'll get through it. So first of all, describing sets. What is a set? Any group or collection of objects is called a set. That's pretty broad, right? Any group or collection of objects, that's a set. There are 2 basic ways we can describe sets, with words and by the roster method. So here's how I might describe something in words. I might say the set of even numbers between 1 and 9. But then here's how it looks in the roster method. Or I might say the set of US states bordering Pennsylvania. And here's how it looks in the roster method. So in the roster method, I literally list out the members of the set, and I put them between braces. So the curly delimiters outside, those are braces. And then I write 2, 4, 6, 8, and I separate the elements of my set with commas. Notice, let me just put a few words in here for delimiters. The curly ones, like what goes outside of a set, those are braces. And the square ones, sometimes you see those are called brackets. So we say brackets for the square ones. And then the most common ones, of course, the parentheses. So we have 3 different words for 3 different kinds of delimiters. Sometimes people mix them up. Very often people mix them up, but try to be consistent with them. When we talk about sets, the delimiter for a set, those are braces. The objects that belong in a set are called the elements, or the members of the set. So I have 6 elements in this second set. Those elements are the 6 states that border Pennsylvania. And in the first case, I have 4 members in that set. Order does not matter in a set. It doesn't matter how I write those 6 states. What really matters is just membership, which states are in the set and which states aren't. Also, repeats. Sets don't count repeats. So if I have this weird looking thing on the left, like 1, 3, 5, 1, 3, 3, 3, 5, 3, 1, really that's just the set that contains 1, 3, and 5. That set has 3 elements. How do I indicate membership? Here's a little bit of notation. Suppose I have this set, 2, 4, 6, 8, and I give it a name. I'm going to call it S. I can say 4 is an element of S, and I use this funny looking E symbol. That means is an element of. So 4 is an element of S. And you can see that's true, right? Because there is 4. 4 is in that set. Or you can write 7 is not an element of S. And when I look at that set, 7 is not there, so that is a true statement too. Sometimes we also just say very quickly, 4 is in S, or 7 is not in S. Now, in mathematics, the kinds of sets that we use are often sets of numbers. There are some standard names for standard number sets. The most basic, perhaps, is the set of natural numbers. So we write this with this funny looking N. That's called a blackboard bold N, or a double struck N. Now when I actually write it by hand, this is how I write the N when I write it out. And it's the set that begins with 1 and then goes 2, 3, 4, 5, on and on and on. And that's what the 3 dots means. That's an ellipsis. When you see the ellipsis, it means whatever pattern you see, keep doing that forever and ever and ever. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, on and on and on, forever and ever without end. That is the set of natural numbers. After that is the set of integers, and curiously, the symbol for this is a Z, and when I write this by hand, I actually write my Z that way, so it looks kind of cool. Incidentally, this actually comes from the German word Zahlen. A little bit of trivia there. And it's kind of like the natural numbers, but it also includes 0, and it also includes the negatives of all those. So this is an infinite set in 2 directions. So on the left, I have the 3 dots. So I'm thinking all those negative numbers, if I continue on to the left, -1, -2, -3, -4, -5, -6, -7, down and down and down and down, forever and ever. And then on the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, all and on and on and on, up forever and ever and ever. Infinite in both directions, positives and negatives. Rational numbers, so I write my rationals by hand like that. And this is the set of all fractions of integers, things like 7/13, negative 21/5. It's okay to have negative. 9/1. It's okay that 9 over 1 reduces. 9 over 1 is a fraction, and that equals 9. So in fact, 9 is a rational number. Now we come to the real numbers, which is basically like all numbers. It's all numbers on the number line. And when I write this out by hand, that's how I do it. So for us, we think of the real numbers as really representing all possible numbers. No gaps, no holes, the entire number line filled in forever and ever and ever. There is one set that we haven't talked about yet. That's the set of irrational numbers. Basically, it's every real number that isn't rational. So it turns out that not every real number can be represented as a fraction of integers. And there are some kind of more weird ones like pi and the square root of 2. Those are irrational numbers. No matter how you try, you'll never be able to write pi as a fraction of 2 integers. You'll never be able to write the square root of 2 as a fraction of 2 integers. All right, so let's practice set membership with some of these basic number sets. Give these things a try. Pause the video, do your best, and then unpause when you are ready to check your work. All right, give it a try. And we're back. Let's see how you did. True or false? 4 is an element of this set. Yes, that's true. -5 is in the natural numbers. No, that's false. Natural numbers start at 1 and then go up. 1/2 is not an element of the integers. That's true. The integers are just like the naturals, but positive and negative and including 0. So 1/2 is not in the set of integers. 4 is an element of the rational numbers. That is true also, because 4 is the same as 4 over 1, and I can see that I have a fraction of 2 integers, and so that is a rational number. Use the roster method to write each of the given sets. All right, let's give this a try. If you'd like to pause and try, go to it. Otherwise, here we go. Let's jump right in. A, the set of natural numbers less than 100. How would we write this in roster notation? Well, I'll start with my open brace. The natural numbers begin 1, 2, 3. Now, I don't really want to write all of these numbers. So what I can do is I can use the ellipsis, write my 3 dots, and then I'll just stop when I need to stop. And these numbers need to be less than 100, so we'll go all the way up to 99. There we go. B, the set of negative integers greater than -4. All right, so we're talking about integers. Integers can be negative, so that's okay. And so what are my integers greater than -4? Well, maybe things like -3, -2, -1, 0, 1. Oh, let's see here. Yeah, okay, on and on. 2, do I need to stop? I don't think so. The set of negative integers. Whoops, I do need to stop. So I don't want 0 and all of those other guys. So it looks like maybe just the set containing -3, -2, and -1. How about the set of positive integers less than -4? Now, this is going to be a little bit weird, right? Positive integers less than -4? It can't be done. There are no positive integers less than -4. One way to indicate this is with a brace that opens and a brace that closes and nothing in between. An empty set, a set that contains nothing. D, the set of rational numbers between 0 and 1. All right, this one's going to be tough. And I actually can't do this. There's too many of them, right? There's infinitely many rational numbers between 0 and 1. Things like 5/27 or 572, I don't know, 3,941. There's a fraction between 0 and 1. I couldn't possibly list them all. And how do I even establish a pattern so I could use the ellipsis? It's not clear. So how do we describe such a set? And the answer is with set builder notation. So set builder notation gives us a way of describing more complicated sets easily. It kind of takes a set description in words and turns it into mathematical notation. Consider this description in words. The set of all elements x such that x is a natural number and x is greater than 7. Pause the video if you need to. Can you figure out what kind of a set that is, what that looks like? Here's how we would change that description into mathematical notation, and this is the set builder notation. I start with a brace, and I read the set, and then x, the set of all elements x, and then I write a colon. And when you write the colon, you read that as such that. So it's the set of all elements x such that x is an element in the set of natural numbers, there, and x is greater than 7. So by starting with a brace, ending with a brace, put the x in front, and then with a colon, and then sort of its description there, that gives us set builder notation and is a nice way of describing sets. So give this a try. Take a look at these 4 sets. They're written in set builder notation. See if you can figure out the set it's describing and maybe write them out in roster notation. Pause the video, give it a try, and then unpause when you are ready to check your work. All right. So let's see how you did. A, the set of all x such that x is a natural number and x is less than 5. 1, 2, 3, 4. Just like that. The set of all x such that x is an integer and x is less than 5. Well, let's see. I don't really have a lowest number, so maybe I'll even start with the ellipsis. -2, -1, 0, 1, 2, 3, but then I will stop when I get to 4 because I don't want to reach 5. So there we are. That's a nice way of writing the set of all integers x such that x is less than 5. Order doesn't matter, so maybe it's more natural for you to think about it this way. You could go 4, 3, 2, 1, 0, -1, -2, -3, and then put your dots on that side. That's okay. That's another good way of writing this set. C gets a little tricky. Look, I'm not just writing n before the colon. I'm writing n plus 0.1. But where do I get my n's from? Oh, my n is taken from all natural numbers. So I read this as the set of all n plus 0.1 such that n is a natural number. So I'm thinking, what can n be? N is going to be 1, 2, 3, 4, and so on. But I don't want those numbers 1, 2, 3, 4. I want 1 plus 0.1, and 2 plus 0.1, 3 plus 0.1, 4 plus 0.1. And so what I end up with is 1.1, 2.1, 3.1, 4.1, and so on, forever and ever. How about this one? The set of all 10k such that k is a natural number and k is less than or equal to 4. What I often do in these problems is I look at the description to the right of the colon first, and I think, what can k be? K is going to be the numbers 1, 2, 3, and 4. That's what k can be. And then I look to the left of the colon and I see, what is the form of the number? It's 10k, so it's 10 times 1, 10 times 2, 10 times 3, 10 times 4. So the answer I get there is 10, 20, 30, 40. There we go. Use set builder notation to write the following sets. So here we go. This was the problem that stumped us earlier when we only knew the roster method. The set of rational numbers between 0 and 1. So I might write this as the set of, how about r, such that r is an element of the rational numbers, and how about 0 less than r less than 1. There we go. So it's the set of all r such that r is a rational number and r is strictly between 0 and 1. How about this? The set of integers greater than -200 and less than 1,000. Maybe something like this. X, the variable doesn't really matter. You can, how about we'll go crazy. How about m? We haven't used m yet. The set of all m such that, let's see, m is an integer and Let's say they have to be greater than negative 200. So negative 200 is less than m, and m has to be less than 1,000. Less than 1,000. There we go. A few more definitions. The empty set, or the null set, they both mean the same thing. That's the set that contains no elements. We had seen that before when I had some braces with nothing in between them. Here's this other notation. Sometimes you see like this 0 with the slash through it. That's another way of writing the empty set. Maybe I like the two braces because it just shows us that we're really talking about a set. But you do often see the other notation too. Just remember, it's not really a number. It doesn't really represent 0. It really represents a set. It's the set that contains nothing. Here's an example. The set of natural numbers less than negative 4. There is no such number in that set. So this description here, that is the empty set, or the null set. The cardinality of a finite set, that's the number of elements in the set. Sometimes we think about it as the size of the set. And to indicate the cardinality of set A, I can either put vertical bars around it, kind of like absolute value, or sometimes you see this, a little n with parentheses and the A inside. So like n for number, the number of things in it. So if A is the set 1, 4, 6, 9, then the cardinality of A is 4. And I can write by using the vertical bars, or I could write it this way, n of A equals 4. The cardinality of A is 4. How about this one? Find the cardinality of each of the following sets. I'll give you a minute, try your best, and then start again when you are ready to check your work. All right, let's see what we have here. First one's easy, the cardinality of J. How about like that? I'll use vertical bars. J equals 2. There are 2 elements in that set, negative 1 and 3. B is tricky. What is the size of that set S? I'm telling you it's tricky. Do you want to change your answer? All right. If you answered 90, you are wrong. The answer is not 90. It's actually 91. Think about it this way. What if I took all the numbers from 1 to 100? 1 to 100. There's 100 numbers in that. 1 to 100. But then I'm taking away the first 9. So 100 minus 9 equals 91. There are 91 elements in that set. How about this? T, the cardinality of T. Well, remember, sets don't count repeats, so there's only 3 elements there. Just to mix things up a little bit, how about if I use the n notation? N of U. The number of elements in here. Cardinality only considers like the high-level elements. There's only 4 things in there. The answer is 4. 4, 5, a set ABC, and 9. So this set is one thing inside of U. This is a little bit strange to have a set that contains numbers and sets, but that's okay. We often have sets that contain sets inside of them. And then K. What is the cardinality of K? The set of all x such that x is a natural number and x is less than 0. Oh, that's the empty set, right? How many things are in the empty set? The answer is 0. The empty set has cardinality 0. Equal sets have exactly the same elements. So in this example, the elements have gotten mixed around, but it's still the same elements, just in a different order. That's okay. And in this second example, remember, sets don't count repeats, so these 2 things really represent both the same set. So how about these 2 sets? Are those equal? The first one is the set of all p such that p is prime and p is less than 10. And then I have the set 2, 3, 5, 7. Well, let's think about my prime numbers. Prime numbers start with 2, not 4. Well, 3, and then 5, 6, no, 7. 7's prime. 8. What about 9? Is 9 prime? No, 9's not prime. Oh, and then we get to 10, and that's it. So my prime numbers less than 10. Ah, look at that. There they are. It's the same thing. So yes, they are equal. And that brings us to the end of our introduction to sets. Some of the basic ideas, what is a set, some basic number sets, using set builder notation, and then some of the vocabulary that surrounds sets as well. That ends this section 2A.